mathematics seminar. Speaker is Colin Defant from Princeton University. We'll talk about structure in stack sorting. As usual, we're going to take the speaker, in this case Colin, out for dinner. As usual, place Evelyn at 6:45. But I need to know if you can come and be standing here right after the talk. Let me know if you can make it.
All right, yeah, so thank you, and thank you everyone for coming. It's great to be speaking here at the famous Rutgers Experimental Math Seminar. So I want to tell you today about a specific topic that I'm studying for my dissertation, and this is a topic that concerns a specific function that I'll call the stack sorting map. Sometimes this is called West's stack sorting map because it was studied in depth by Julian West in his PhD thesis in 1990 at MIT under the direction of Richard Stanley. And when I tell you about this function, you might have the same sort of thoughts that I had when I first saw this, which is it seems sort of arbitrary and maybe a little unmotivated. So I'm going to tell you that I have three motivating reasons for studying this. The first is historical. So this function was essentially introduced in a slightly different form by Donald Knuth in his book The Art of Computer Programming, and his analysis of this led to a lot of very important definitions and theorems and combinatorics, and I'll touch upon a couple of those. The second reason is that there are actually multiple ways of defining this function. I'm going to give you the classical definition, but there's also a simple recursive definition, and there's an interesting definition involving labeled trees. I just don't have time to go through that. And then the third reason is that this function is actually going to give us a dynamical system on the set of permutations of length n. And like you might expect with many dynamical systems, it gets very complicated very quickly when you start to study it. So it looks like everything's just a big mess, and there's really nothing nice you can say. But I'm going to try to convince you today that that's not actually the case, that there's actually a lot of interesting combinatorial structure lying beneath the surface of the stack sorting map. Okay, so that's my goal, but before I do that, let me just make sure we're all on the same page. So for me, a permutation of length n is just an ordering of the numbers from 1 to n, and I'll let S in be the set of permutations of length n. So for example, here's a permutation of length 7. Here's another example of a permutation of length 7. This is the identity permutation of length 7. Identity just means everything's in increasing order. A descent of a permutation is an index I such that the ith entry of the permutation is bigger than the I plus first entry. So it's just a place where the permutation goes down. And as an example, the descents of this permutation are 2 and 6. 2 is a descent because the second entry is bigger than the third, and 6 is a descent because the sixth entry is bigger than the seventh. And pretty much by definition, the identity permutation of length n is always the unique permutation of length n that has no descents, because it never goes down. All right, now I also want to define pattern avoidance in permutations, and this is a huge definition in modern combinatorics. And it says that if we have two permutations, sigma and tau, we'll say that sigma contains the pattern tau if we can find entries in sigma that have the same relative order as tau. They don't have to be consecutive entries, they're just entries in sigma. And if sigma doesn't contain tau, we say that sigma avoids tau. So an example here would be we could look at the permutation 31524 and see that this contains the pattern 2, 3, 1, because if we look at these entries 3, 5, and 2, then their plot sort of has the same shape as 2, 3, 1. You can see sort of 3, 5, 2 has the same shape as 2, 3, 1, and that's why we say that this permutation contains the pattern 2, 3, 1. On the other hand, you can check that this permutation 3, 1, 5, 2, 4 does not have a decreasing subsequence of length 3, and we could express that by saying it does not contain the pattern 3, 2, 1, and so we'll say that it avoids the pattern 3, 2, 1. Okay? All right, so now I'll define this stack sorting map, and this is a function that I'll denote by S. So the whole talk here is about this function S. And this is a function that sends permutations of length n to permutations of length n. And I'll show you how it works with an example. I think that should illustrate the general procedure. So I'll show you how to compute S of 416352. We're going to start by putting 416352 up on the right-hand side of this thing here called the stack. So this is the stack, and at any point in time, the leftmost entry up here wants to come into the stack. But the rule of the stack is you can't have something big sitting on top of something small. You're not allowed to have a number sitting on top of something smaller than it. So I'll go through the example, and I think that'll make things clear. The 4 wants to go into the stack, and that's fine because the stack is empty. And then the 1 wants to come in, which is also fine because 1 can sit on top of 4. Now 6 wants to come in, but 6 can't sit on top of 1 because 6 is bigger than 1. So before 6 can come in, 1 has to pop out. And for the same reason, 6 can't sit on top of 4, so 4 has to pop out. But now 6 can go into the empty stack, and then 3 can go in on top of it. Now 5 can't sit on top of 3, so 3 has to pop out. But 5 can't sit on top of 6, and then 2 can sit on top of 5. And now that we have nothing left to push into the stack, we just empty the stack from top to bottom. So the 2 comes out, the 5 comes out, and the 6 comes out, and we get the output permutation 1, 4, 3, 2, 5, 6. Now, this is a sorting map. The idea is you're supposed to take a permutation, send it through this stack, and as the output, it should be sorted into the identity permutation 1, 2, 3, 4, 5, 6. Now here you can see we did not get 1, 2, 3, 4, 5, 6. We got something else. And so you could think, okay, it didn't work. But the idea is we could just take the output permutation that we did get and send it back through the stack. And if we don't get the identity, send it through again, and again, and again, and again. You just iteratively apply S until eventually you get to the identity. You will eventually get to the identity, that's guaranteed. And so the question is just, how long does it take to get there? And this leads to the notion of a t-stack-sortable permutation. So we say a permutation is t-stack-sortable if it requires t or fewer iterations in order to get to the identity. In other words, pi is called t-stack-sortable if s to the t of pi is the identity, where s to the t denotes s composed with itself t times. And I'm going to let w sub t of n be the number of t-stack-sortable permutations of length n. Right, now, the first result in this area is really due to Knuth, who showed that a permutation is one-stack sortable if and only if it avoids the pattern 2, 3, 1. And this is sort of just a slight variant of the theorem that initiated the study of pattern avoidance in permutation. So from a historical point of view, this is a really important theorem. And he also showed that the number of 2, 3, 1 avoiding permutations of length n is the nth Catalan number, which I've denoted here by c sub n. So this is just 1 over n plus 1 times 2 n choose n. And so we now know that w sub 1 of n, the number of one-stack sortable permutations of length n, is just the nth Catalan number. Now, as I mentioned before, Julian West studied this stack sorting map in depth in his thesis, and he gave a characterization for two-stack sortable permutations. And he also gave a conjecture for the number of two-stack sortable permutations of length n, and this was proven a couple years later by Doron and Zauberger. So Zauberger showed that w sub 2 of n is given by this expression here. And now you could ask, okay, what about 3-stack sortable permutations? What about 4-stack sortable permutations? And so on. It turns out in those cases we have no idea how to find an explicit formula for these numbers w sub t of n, but there are some things we can say. So the best known upper bound in general is due to, or it follows from the theorem of West and Stankova, and it says that w sub t of n is at most t plus 1 to the power of 2n. However, if you, Bona has conjectured that w sub t of n should be at most t plus 1 n choose n, and if you go through the asymptotics of this using Stirling's formula, you can check that this is much stronger than what's known up here. So Bona actually introduced me to the stack sorting map, and he said it would be interesting if you could find better upper bounds for these numbers. And I was able to do that in the cases t equals 3 and t equals 4. I showed that w3 even is less than 12.53 to the n, which improves the previous bound of 16 to the n, and w4 of n is less than 21.97 to the n, which improves the previous bound of 25 to the n. And also, just a couple months ago, I realized that I could find actually a lower bound for the number of 3-stack sortable permutations of length n. So basically what this is saying is that the number of 3-stack sortable permutations of length n grows like some constant to the power of n, and that constant is at least roughly 7.97. That's basically what this is saying.
So for t equals 1 is 4, and for t equals
yes.
2?
For t equals 2, it's 6.75, and then these are bounds for, right. Yeah. So, okay, I want to say a little bit about this lower bound. So I'm going to take a permutation pi of length n. I'll write it as pi 1 through pi n. I'm going to define the tail length of pi to be the smallest non-negative integer L, such that the n minus Lth entry of the permutation is not n minus L. So an easy way to see what I mean by this is we can look at this example, 3, 1, 2, 4, 5, 6, 7, 8, 9. This ends in the tail, which is 4, 5, 6, 7, 8, 9, sort of this tail where everything's in the correct position. And so the tail of this permutation is 4, 5, 6, 7, 8, 9. That has length 6. So the tail length of this is 6. And I'm going to let TLS of pi be the tail length of S of pi, where again S is this stack sorting map. So we look at the tail length of S of pi. And there's this other statistic that I want to talk about called the Zauberger statistic. And this is the largest number m, such that the numbers n minus 1, all the way down to n minus m plus 1 appear in decreasing order in the permutation. So this really emerged first in Zauberger's work on two-stack sortable permutations, and essentially what he does, in a very rough sense, is he counts two-stack sortable permutations according to this additional statistic Zeil, and then this gives him a bivariate generating function equation, and he has to remove an additional catalytic variable in order to get this formula for w sub 2 of n. So actually recently I found that I could give a new proof of this formula for w sub 2 of n, and it does sort of the same kind of thing where, again, we want to count two-stack sortable permutations according to an additional statistic and then remove some catalytic variable. But this time, instead of using the statistic Zeil, I use the statistic TLS. And the nice thing about this is that it generalizes and allows me to get a lower bound for the number of 3-stack sortable permutations of length n, and it also allows me to count some other things that I'll talk about toward the end of the talk.
You should call it def or defant.
There's something else that I call def for deficiency. It looks like Defant though, but yeah, right, I see it. So okay, I wanted to say that there's this, there's an interesting relationship between xyl and TLS actually. It's that xyl of pi is actually the minimum of TLS and Rmax of pi, where Rmax of pi is the number of right-to-left maxima in the permutation. A right-to-left maximum in a permutation is just a number in the permutation which is bigger than everything to its right. So you count up the number of right-to-left maxima in the permutation, that's Rmax of pi, and then there's this cute little identity that shows that these are sort of related in some sense. Okay. Now, I also want to talk about something called the fertility of a permutation. This is a definition due to West from 1990. He defined the fertility of pi to just be the number of preimages of pi under the stack sorting map. And Bousquet-Mélou defined a permutation to be sorted if its fertility is positive. In other words, it has at least one preimage under the stack sorting map. Of course, this is the same as saying it's in the image of the stack sorting map. Okay, so there's something complicated in these definitions. The fertility of a permutation is just the number of preimages of the permutation under the stack sorting map, and saying a permutation is sorted is the same as saying it has at least one preimage. Now, West was able to compute the fertilities of some very specific types of permutations. For example, if you take the identity permutation of length n, and you switch two consecutive entries, that's an example of a permutation where West can compute the fertility, but again, that's a very specific type of permutation. And Bousquet-Mélou gave an algorithm to determine whether or not a given permutation is sorted. In other words, if you give her a permutation, she can tell you whether or not the fertility of this permutation is 0. But if it's non-zero, she doesn't know how to tell you what it actually is. And she says it would be interesting to find a general method for computing the fertility of any given permutation. So that's actually what I was able to do. I found a method for computing the fertility of any given permutation. And I'm going to go through this method very quickly on the next slide. I realize that I'm going through it very quickly, so it's okay if you don't digest every single word that I'm going to say, because I'm going to try to highlight the main points to keep in mind at the end of the slide. But the method involves studying new combinatorial objects that I've defined that I call valid hook configurations. So to define a valid hook configuration of a permutation, we start by plotting the permutation. This is a plot of the permutation 2, 7, 3, 5, 9, 10, 11, 4, 8, 1, 6, 12, 13, 14, 15, 16. Once we've plotted this permutation, we can draw what I call hooks on this plot. So a hook is where I start at one of these points, and I move vertically upward, and then I move horizontally to the right to connect with another one of the points. So here you can see I've drawn 3 hooks on this diagram, and this gives me a configuration of hooks. Now, there are these 3 magical properties that a configuration of hooks could satisfy. I'm not going to tell you what they are just because of time constraints, but there are these 3 magical properties, and if my configuration of hooks satisfies these properties, I call it a valid hook configuration. So it turns out that this is an example of a valid hook configuration of this permutation. And once I have a valid hook configuration of a permutation, this will induce a coloring of this diagram. The way that we color the diagram is we start by drawing a sky over the entire diagram, and you color the sky blue. Okay, you have to color the sky blue, that's important. Then once you've done that, you can color all of the hooks with arbitrary distinct non-blue colors. All I mean by this is you color all of the hooks with different colors, and it doesn't matter what colors you use, as long as you don't use blue because you already used blue for the sky. Now once you've done this, this will induce a coloring of all of these points. The way that you color a point is you go to that point and you tell it to look upward. And whatever color it sees, it becomes that color. For example, the 5 looks up and sees the green hook, so it becomes green. The 2 looks up and sees the sky, so it becomes blue. Now, there are a couple of caveats here. One is that if a point has the horizontal part of the hook coming into it, it doesn't get colored. That's why the 11, the 13, and the 15 here are black. They do not get colored because they have horizontal parts of hooks coming into them. And then the second caveat is that the points cannot see the vertical parts of these hooks. The vertical parts of the hooks are invisible to the points, which is why the 7 doesn't see the green hook. That's why the 7 is blue, it sees the sky. And similarly, that's why the 8 here is red and not orange. But the point is, it's some way of coloring this diagram, which is induced from this valid hook configuration. And once I have this, I can read off the number of points of every color. In this example, there are 3 blue points, 4 green points, 3 red points, and 3 orange points. So I get the integer composition 3, 4, 3, 3. By the way, for me, a composition of a number is just a tuple of positive integers that sums up to that number. So this is a composition of 13 because 3 plus 4 plus 3 plus 3 is 13. And I would say that this is a composition of 13 into 4 parts, which just means that there are 4 numbers in the tuple. Now, I could have chosen a different valid hook configuration of this permutation. That would have given me a different coloring of this diagram, which would have given me a different integer composition. So I'm going to say that any composition that I could have obtained in this way from this permutation is called a valid composition of the permutation. And I let V of pi be the set of all valid compositions of the permutation pi. Now, okay, the reason that I've done all this is that I now have a formula for the fertility of the permutation pi. It's just given by a sum of products of Catalan numbers. So the C's here are the Catalan numbers. This is a product of Catalan numbers. We understand pretty much everything we need to know here about Catalan numbers. And we know how to take products, right? We know how to multiply things. So products of Catalan numbers are not really mysterious things. The sort of mysterious part here is that the sum is ranging over this set of valid compositions of pi. And if I just give you a permutation, it's not immediately obvious what the set of valid compositions is going to be. So for that reason, this is not going to give us full information about everything we want to know about the stack sorting map, but it's still a useful formula, and in the rest of the talk I'm going to give you some applications of this formula. But before I do that, I just want to mention that for many applications, you don't actually need to know how to find the set of valid compositions. I sort of described it here. I said, okay, you do this coloring, you read off the number of points of every color. For many applications, including the application of finding an upper bound for the number of 3 stack sortable permutations, you don't actually need to know how to do this. All you actually need to know is what I've written here, which is that if pi is a permutation of length n, and let's say pi has k descents, so there are k places where it goes down, then there exists a set V of pi. I'm not telling you how to find it, I'm just saying there exists a set V of pi of compositions of n minus k into k plus 1 parts such that this formula holds. So one of the important points here is that it turns out that every valid composition of pi is actually a composition of the number n minus k into k plus 1 parts. So for example over here, this is a permutation of length 16, so n is 16. And you can check that it has 3 descents, so k is 3. And as I said before, this is a composition of 13, which is 16 minus 3, into 4 parts, and 4 is 3 plus 1. So in general, all of the valid compositions of pi are going to be compositions of n minus k into k plus 1 parts.
Also get upper bound for...
Right, yeah. So, okay, now I want to give some applications of this. And so I'm going to start with what I call uniquely sorted permutations. So remember, Bousquet-Mélou defined a permutation to be sorted if it has at least one preimage under the stack sorting map. I'm going to say it's uniquely sorted if it has exactly one preimage. And so I have a theorem with Engen and Miller, and this is basically just a consequence of what I wrote over there, but I want to state it here as a theorem. And this says that a permutation of length n is uniquely sorted if and only if it's sorted and it has exactly n minus 1 over 2 descents. So one thing this is telling you is that there are no uniquely sorted permutations of even length. Because, right, if n is even, then this is not an integer, so it can't be the number of descents of the permutation. So there are no uniquely sorted permutations of length 2, 4, 6, 8, 10, and so on, but there are uniquely sorted permutations of length 1, 3, 5, 7, 9, and so on, and you can ask, well, how many are there? And so it turns out that this is given by something called LaSalles sequence. You don't have to digest what this is. This is some recurrence relation. It's not really too important what it is, but it's defining some sequence A sub m. And I don't know exactly how this came about. Maybe Professor Zauberger can tell me more about this after the talk. But I think, as far as I'm aware, what happened is somehow Professor Zauberger found this and wrote this down and computed the first few terms of this sequence and said it looks like they're positive, which is not at all obvious from the definition because of these alternating signs. So he says it looks like they're actually positive, and not just positive, it looks like they're actually increasing. And so he states this as a conjecture that the terms in this sequence are positive, and not just positive, but actually increasing. And then this was proven by LaSalles, which is why it's called LaSalles sequence. However, LaSalles' proof is completely algebraic, and it doesn't give us any kind of a combinatorial reason why we might expect these numbers to be positive and increasing. In other words, we might think maybe they count something. Maybe there are some objects that are counted by these numbers. And this is originally found, this is the case, this is originally found by a guy named Josua Verger, who was studying something called free probability theory. This is basically like a non-commutative analog of regular probability theory that shows up in the context of random matrix theory, among other things. And he was studying this, and this led him naturally to this combinatorial interpretation of LaSalles sequence involving set partitions and acyclic orientations of certain graphs and Tut polynomials, and I'm not really going to go into the details of what this is. It's just some combinatorial interpretation of LaSalles sequence, and it's coming from this free probability theory thing. Now this is useful for us because Engen, Miller, and I were able to find a bijection, and this bijection goes from the set of valid hook configurations. Remember, these are these new objects that I sort of tried to define for you a few slides ago. So we have a bijection that goes from valid hook configurations to a set of objects that Bousquet-Mélou was studying. And then we show that if you restrict this bijection to the set of valid hook configurations that you can draw on uniquely sorted permutations, you end up getting a bijection between uniquely sorted permutations and a special subset of the objects that Bousquet-Mélou was studying. And as a consequence of this, first we can actually count these valid hook configuration things. We now know that the number of valid hook configurations that you can draw on permutations of length n is given by negative k sub n plus 1 of minus 1, where k sub n plus 1 of lambda is the n plus first cumulants of the free Poisson law with rate lambda. It's not really important what this is. Basically, it's some free probability theory thing, but I think it's sort of interesting that this free probability theory thing is actually counting these new objects that I've defined. And then the other part of the consequence here is that we now know that ak plus 1, remember this is the k plus first term in LaSalles sequence, this is the number of uniquely sorted permutations of length 2k plus 1. So we've now counted uniquely sorted permutations, and we have a new combinatorial interpretation of LaSalles sequence. All right, now I want to refine LaSalles sequence for you a little bit. So remember, ak plus 1 is the k plus first term in LaSalles sequence. It's the number of uniquely sorted permutations of length 2k plus 1. I'm going to define ak plus 1 of L to be the number of uniquely sorted permutations of length 2k plus 1 in which the first number is L. This is sort of a weird thing to do because usually when you look at permutation statistics, you look at things like the number of descents or the number of inversions or the major index or the number of peaks or something like that. It's not typical to look at the first number in the permutation, but that's because it's usually not very interesting. Here it actually turns out to be pretty interesting because we've shown that the sequence ak plus 1 of 1, ak plus 1 of 2, ak plus 1 of 2k plus 1 is actually symmetric. So it's palindromic, it reads the same forward and backward. And this is really not obvious from the definition of a uniquely sorted permutation. You really have to, I think, trace through our bijection in order to see why this is the case. And it's also a little bit counterintuitive because if you think about it, the things we're counting here are sorted permutations. They're in the image of the stack sorting map, and the stack sorting map is a sorting map. It's supposed to take a permutation and send it to something closer to the identity. So you should expect things in the image should be somewhat close to the identity, meaning they should start with somewhat small numbers. But this is saying that the number of these permutations that start with 1 is the same as the number that start with 2k plus 1, and the number that start with 2 is the same as the number that start with 2k, and so on. And of course, the reason that we're getting this symmetry is because we're not just counting sorted permutations, we're counting uniquely sorted permutations.
So it's not all obvious.
Right, it's not really obvious from the definition.
It's very surprising.
Yeah, right, it's surprising, and what's really happening here is that we're requiring that these permutations have at least one preimage under the stack sorting map, but also at most one preimage. And this balance between having at least one preimage and at most one preimage ends up giving this perfect symmetry in these sequences. And we've also conjectured that these sequences are unimodal, and actually more than just unimodal, what's called log concave. We haven't been able to prove this though, so I'm not going to say too much about that. That's just a conjecture. Okay, so these are uniquely sorted permutations. We could go to the next step and say, well, what about doubly sorted permutations? These would be permutations with fertility 2, so they have exactly 2 preimages under the stack sorting map. What can we say about these? Well, if you go to what I wrote over there, you can check that there are no doubly sorted permutations of odd length. But there are doubly sorted permutations of even length, and if you count them, you get the sequence 1, 3, 31, 1186, and so on. So I put this into the online encyclopedia of integer sequences, and nothing came up. So it's possible that there's not something nice here. Maybe there's some interesting structure. Maybe this is an interesting sequence for some reason. I don't really know. When I put it into the OEIS and nothing came up, I thought, okay, I'm not really going to think about this too much. I'll just go to the next step, which would be triply sorted permutations. These would be permutations with fertility 3, so they have exactly 3 preimages under the stack sorting map. Maybe these are interesting. What can we say about these? Well, it turns out they don't exist. So you cannot find a permutation that has exactly 3 preimages under the stack sorting map. And I can actually prove this to you pretty easily if you...
It's a 0 sequence.
Right? Yeah, yes.
It's all different.
It is in the OEIS, yes. The 0 sequence, right. So I can actually prove this to you pretty easily if you believe what I wrote here. So the difficult part here is sort of getting to this step. But once you have this, it's sort of a cute little consequence to see that there are no permutations with fertility 3. And so I'll go through this now. I'll say, let's assume, by way of contradiction, that we have a permutation pi with fertility 3. So let's say pi has length n, and we'll say it has k descents. So I'm saying that this expression here should be 3. Now this is a sum of products of Catalan numbers. The first few Catalan numbers are 1, 2, 5, 14, 42, and so on, and they keep growing. So you can see the only way we're going to get a sum of products of Catalan numbers to be 3 is if the only Catalan numbers we actually use are 1 and 2. In other words, this sum is either 1 plus 1 plus 1 or 2 plus 1. In either case, one of the products here has to be 1. So one of these products must be 1. And that can only happen if it's a product of a bunch of C sub 1s. So one of the products here has to be C1 times C1 times C1 times dot 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 times C1, which means that one of these valid compositions has to be just a bunch of 1s. Okay, so one of the valid compositions is just a bunch of 1s. But remember, every valid composition of pi is a composition of n minus k into k plus 1 parts. So if we have a bunch of 1s forming a composition of n minus k into k plus 1 parts, that means we've written n minus k as a sum of k plus 1 1s, which means that n minus k equals k plus 1. So now we know that n minus k equals k plus 1, but now we can go backward. We can say, okay, n minus k equals k plus 1. What are the possible compositions of n minus k into k plus 1 parts? Well, these are just compositions of k plus 1 into k plus 1 parts, and there's only one of those, namely a bunch of 1s. So there's only one possible composition of n minus k into k plus 1 parts, which is a bunch of 1s, meaning there's only one possible valid composition of pi, namely a bunch of 1s. So there's only one term in this sum, and that one term is just a product of a bunch of 1s. So the whole thing here is just 1, which is not 3. We assumed it was 3, we've deduced that it's 1, and that's the contradiction. So that's why you can't have a permutation with fertility 3. Again, the difficult part here is getting to this step, but once you have this, it's sort of just a cute little consequence. And so this leads me to define what I call a fertility number. So I'm going to say a non-negative integer f is a fertility number if there exists a permutation whose fertility is f. So what I was saying on the previous slide is that 3 is not a fertility number. I could call this a non-fertility number if you want. Actually, I'm going to call it an infertility number because infertility is already a word in the English dictionary. And so we have fertility numbers and infertility numbers, and we can ask, what are these? What are these numbers? Well, 0 is a fertility number because it's the fertility of the permutation 2, 1. That's an example. Okay? 1 is a fertility number because, for example, it's the fertility of the permutation 1, right? Just 1. Actually, we've seen that there are a lot of permutations with fertility 1. These are the uniquely sorted permutations. They're counted by LaSalles sequence, so we know that actually there are a lot of these. 2 is a fertility number because, for example, it's the fertility of the permutation 1, 2. That's one example. 3, we said, is an infertility number. 4 is a fertility number because it's the fertility of the permutation 2, 1, 3, 4. That's one example. 5 is a fertility number because it's the fertility of the permutation 1, 2, 3. 6 is a fertility number because it's the fertility of the permutation 3, 2, 1, 4, 5, 6. 7 is actually an infertility number. So you can check, basically along the same lines as what we did with 3, maybe with an extra case or so, you can check that 7 is also an infertility number. And okay, so now you can keep going, you can compute more of these. You can find that 8 is a fertility number, 9 is a fertility number, 10 is a fertility number, but 11 is not. And 12 is, 13 is, 14 is, but 15 is not. And 16 is, 17 is, 18 is, but 19 is not. And 20 is, 21 is, 22 is, but 23 is not. Okay, so yeah, at this point, I guess, this is the experimental math seminar, so I guess you're supposed to get some data, look for some patterns, and it looks like there's a pretty striking pattern here, whereas it looks like the infertility numbers are just the non-negative integers that are congruent to 3 mod 4. So you can compute a few more, 24, 25, and 26 infertility numbers, but so is 27. So, okay, the pattern breaks here at 27, and so it's not, the pattern that we were seeing. You can compute a few more of these, 28, 29, and 30 are fertility numbers, and now you can say, okay, what can you say about the set of fertility numbers? Is there any pattern that actually continues to hold that you can actually prove? I should mention that I've conjectured that there are infinitely many infertility numbers. I haven't actually been able to prove this, but it looks like there should be infinitely many of these infertility numbers. There are definitely infinitely many fertility numbers, but okay, so now you can say, well, okay, what can you actually prove? Well, one thing is that it turns out the set of fertility numbers is actually closed under multiplication. So if you multiply 2 fertility numbers, you get another fertility number, which I think is kind of weird. I mean, think about how we got here. We started by defining this weird stack sorting thing, and we put these numbers through this stack, and we say, okay, this goes in and this comes out according to what's bigger and what's smaller, and I say I'm going to look at this as a dynamical system and look at the number of preimages of a permutation in this dynamical system and say a fertility number is a number that is the number of preimages of some permutation in this dynamical system, and you think, well, okay, why would you do that? And then somehow it turns out that this is closed under multiplication, so it forms a multiplicative monoid, if you will. But, I don't know, I think it's kind of interesting. Another thing you can ask is, why is 1 a fertility number? Well, it's the fertility of the permutation 1, right? Just 1. But you could think, okay, that's kind of a dumb example. Throw that away. Is 1 still a fertility number? Well, sure. It's the fertility of the permutation 2, 1, 3. And you say, okay, well, that's also a dumb example. Throw that away. Is 1 still a fertility number? Sure. In fact, we've seen that there are a lot of permutations with fertility 1. These are the uniquely sorted permutations. They're counted by LaSalles sequence. So you can ask, does this happen in general? And the answer is yes. If F is a fertility number, then in fact there will be infinitely many permutations with fertility F. So once F is the fertility of one permutation, it'll be the fertility of infinitely many. Okay, now again, on the previous slide we had this pattern we were observing where it looked like the infertility numbers were just the non-negative integers that were congruent to 3 mod 4. We said this is false because 27 is a counterexample, but this pattern is actually 2 separate statements. One statement is every non-negative integer that's congruent to 3 mod 4 is an infertility number. This is false because 27 is a counterexample.
So how far do you know then?
Actually just like 33 or something like that, 34. Yeah, so not too much further, but I think there should be infinitely many. But I'll say something about that. But okay, so the converse of the statement that I was saying is that every non-negative integer that is not congruent to 3 mod 4 is a fertility number. And this is true. So every non-negative integer that's not 3 mod 4 is a fertility number. And so this tells you that the lower asymptotic density of the set of fertility numbers, by the way, when I say lower asymptotic density, I really mean density. I haven't actually proven that this set has a density in the sense of a limit existing, so I have to say lower asymptotic density just to be mathematically formally correct, but I really mean density. But anyway, the lower asymptotic density of this set of fertility numbers is at least 3/4, but you can do a little bit better because we know that 27 is a fertility number. You can also check that 95 is another fertility number that's congruent to 3 mod 4. And we know that fertility numbers are closed under multiplication. So you can take 27 and 95 and multiply them by a bunch of other fertility numbers and get a bunch of new fertility numbers. And this allows you to show that this lower bound is at least roughly 0.7618. Yeah. Okay, so you can bump it up a little bit higher than 3/4. As I said before, the smallest fertility number that's congruent to 3 mod 4 is 27. And then the last thing I want to say here is, okay, let's say F is a fertility number. This means that there's some permutation whose fertility is F. But how far do I have to go searching before I actually find that permutation? Well, one answer, and I don't know if this is the optimal answer, but one answer is that if F is a fertility number, then there exists a permutation whose fertility is F that has length at most F plus 1. I've actually conjectured that you can replace the F plus 1 here by something that's little o of F, but so far what I know is F plus 1. And so what this is saying is basically, okay, let's say I want to know, is 63 a fertility number? I actually don't know. I do not know if 63 is a fertility number or not, but let's say I want to know. This says all I have to do is compute the fertilities of all the permutations of length at most 64, right? Okay, yeah, so this is not really a feasible thing to do. You can't just compute the fertilities of all the permutations of length at most 64. There are way too many of them. But you could think, well, maybe you could do some kind of a clever argument to reduce the computations down to something that a computer could handle. So that's sort of the idea here. This is saying that determining whether or not a given number is a fertility number or not is a finite problem, but it could be a very large finite problem unless you do some additional work to reduce the computations down to something that a computer or a human could handle. And I also wanted to mention that I've conjectured that the second smallest fertility number that's 3 mod 4 is 95, but also I haven't proven this. Okay. Now, I want to go back to actually counting things. So I'm going to let AV sub n of tau 1 through tau r be the set of permutations of length n that avoid the patterns tau 1 through tau r. So remember we have this notion of pattern avoidance and permutations, and I'm going to let AV n of tau 1 through tau r just be the set of permutations of length n that avoid all of these patterns. And I want to look at the total number of preimages of all of these permutations under the stack sorting map. So for example, we can look at the total number of preimages of all the permutations of length n that avoid 1, 2, 3. This turns out to be 0 if n is at least 4, and that's not too hard to show, so this isn't really that interesting, and we can move on. We can look at the total number of preimages of all the permutations of length n that avoid 2, 1, 3. This turns out really to be the same as counting 1 stack sortable permutations, which Knuth did in 1968, and so this is just the nth Catalan number. We could also look at the total number of preimages of all the permutations of length n that avoid 2, 3, 1. This turns out to be the same as counting 2 stack sortable permutations, which Zalberger did in 1992. And so it's given by this formula here. Now actually much more recently, Bouvelle and Guibert showed that if you look at the total number of preimages of all the permutations of length n that avoid 1, 3, 2, you get the same numbers as with 2, 3, 1. And this is not for some trivial reason. There's not some trivial symmetry that allows you to see that these are the same thing. They actually go through a complicated argument to see why these are the same. And I've also given sort of a new proof of this that generalizes and puts this into a much more general framework of showing when you can have two permutation classes such that their preimages are counted by the same numbers. I'm not going to say too much about that, but this is sort of a more general phenomenon that appears. The same authors looked at the total number of preimages of all the permutations of length n that avoid 3, 1, 2, and they showed it's given by this expression here. This is actually the number of what are called Baxter permutations of length n. So it's sort of interesting that the number of Baxter permutations of length n is also the number of preimages of all the permutations of length n that avoid 3, 1, 2. And then I looked at the total number of preimages of all the permutations of length n that avoid 3, 2, 1. And I was not able to find a formula for this. I don't think anyone has a formula for this, but I was able to show that these numbers grow like some constant to the power of n, and that constant is somewhere between 8.4199 and 11.6569. So there's some room for improvement here, but this is the best that I know so far. Okay, now, a permutation class, by the way, a permutation class is just a set of permutations obtained by avoiding some collection of patterns. So for example, if I say all the permutations avoiding 1, 3, 2 and 2, 3, 4, 1, that's an example of a permutation class. And so I had a professor once tell me that he hated this stack sorting map because the set of two stack sortable permutations does not form a permutation class. And he really loves permutation classes, and so because the set of two stack sortable permutations does not form a permutation class, this merited his hatred for this stack sorting map. But I want to convince you today that even if you really love permutation classes, you can still like this version of this stack sorting map, because it turns out that in many cases the set of preimages of a permutation class is another permutation class. So for example, here are just a bunch of examples. We could look at all of the preimages of all the permutations that avoid 3, 2, 1. That turns out to be the same as the set of the set of permutations avoiding these three patterns of length 5. And here are some other examples. And so what this says is that we can actually use stack sorting and these valid hook configurations that I talked about, and this fertility formula that I have, in order to enumerate some of these permutation classes.
The Julian West has some very complicated characterization of two stack sortable permutations.
Right.
Is that related to this?
It is related to this. In some sense, you can do sort of the same kind of argument to get similar characterizations of other preimage sets. It's just in some senses that in some cases they turn out to be permutation classes. So they're not these weird things that he's had to deal with. Right. Okay, so what this is saying is that in many cases we can actually count some of these things using these valid hook configurations that I talked about. So for example, we could look at the total number of preimages of all the permutations of length n that avoid 1, 3, 2, and 2, 3, 1, and 3, 2, 1. This turns out to be the same as the total number of preimages of all the permutations of length n that avoid 1, 3, 2, 3, 1, 2, and 3, 2, 1, which is the same as the central binomial coefficient 2n minus 2 choose n minus 1. We can also count these according to certain statistics, like the number of descents, or the number of what are called peaks, and we get certain refinements of this enumeration. One interesting thing here is that there was a paper in 2015 that talked about this permutation class, but without referring to it as like the set of preimages of something. They actually just wrote it out as a permutation class and said they conjectured that it was counted by these central binomial coefficients. So what this says is that we can actually use stack sorting as a tool in order to prove a conjecture that was stated without any reference to stack sorting, which I think is kind of cool. We can also look at the total number of preimages of all the permutations of length n that avoid 1, 3, 2, 2, 3, 1, and 3, 1, 2. This turns out to be the n plus first fine number. This is an interesting sequence of numbers. And we can also count these preimages according to certain statistics, like the number of descents or the number of peaks. This gives us certain refinements of the fine numbers. So, we can also look at this. So this is the set of preimages of permutations avoiding 2, 3, 1, and 3, 2, 1. And if we form the generating function of this, this turns out to be 1 over 1 minus xc of xc of x, where c of x is the generating function of the Catalan numbers. And one interesting thing here is that the set of preimages of permutations avoiding 2, 3, 1, and 3, 2, 1 turns out to be this permutation class here. So it's the set of permutations avoiding 2, 3, 4, 1, 3, 2, 4, 1, and 4, 5, 2, 3, 1. And this, I think, was not yet enumerated. So this allows us to enumerate a new permutation class. And also, the other interesting thing here is it was already known that this generating function is the generating function of this other permutation class. So this allows us to say that we can now show that these two permutation classes are what's called Wilf equivalent, which just means that they're counted by the same numbers. And another interesting thing here is that this is...
So one of these types was known before?
Yes, this one was already known, that this is the generating function of this. This is new, and so we now know that this is Wilf equivalent to this. And one of the interesting things here is that this is an example of what's called an unbalanced Wilf equivalence. So there was a paper actually as recently as 2016 that defines this thing called an unbalanced Wilf equivalence. Unbalanced basically means, well, we have a pattern of length 5 here, and there's no pattern of length 5 here, so it's sort of unbalanced, and it's kind of weird that they're counted by the same numbers. And actually this paper just conjectured that these things would exist, and the first example of this, I think, was found as recently as 2017. So this is saying that we can use stack sorting to find a new example of an unbalanced Wilf equivalence.
Is that not balanced because the number of permutations?
Yeah, because like it's not, it's not just like 2 patterns of length 4 and 2 patterns of length 4. There's this other pattern of length 5 there that makes it unbalanced. Yeah. Okay, so we can also look at these. So I'm just sort of picking out a few. I've done a lot of these pre-image set things. But we can look at these 3 pre-image sets, and it turns out they're counted by the same numbers. This is not easy to see. This is actually, I go through a really complicated argument to see why these are the same things. And these are counted by something called the Boolean Catalan numbers. So one of the interesting things here is that there was someone who emailed me a couple months ago. His name's Chetak Hossain. And he had this set of permutations that he was considering. And he said, okay, I have this set of permutations obtained by avoiding certain vincular patterns, whatever that means. And so he had this set of permutations, and he said, it looks like these are counted by these Boolean Catalan numbers. Do you know how to prove this? And I said, it looks like actually what you're describing is exactly the set of preimages of the permutations avoiding 132 and 231. So I said, I have actually already proven your conjecture using stack sorting. And the cool thing here is I don't know how to prove his conjecture without using stack sorting. So again, here's a conjecture that we know that I can prove with using stack sorting that I have no idea how to prove without stack sorting, which I think is kind of cool. Okay, here's a picture that I just threw in here. There's not really a reason for this other than to show you that some of this stuff is kind of non-trivial. This is probably the most complicated picture that appears in any one of my papers, and I kind of just wanted to show you like sort of what's going on. I don't know. It's a commutative diagram with these valid hook configurations. I think it's kind of colorful and pretty, so I just wanted to put it here. And it took me a long time to make, so I wanted to do something with it. Also, this tells you I lied to you earlier when I said you have to color the sky blue. Sometimes it's more convenient to color it red or orange. And this is basically just to make it easier to define the maps that are going on here. But anyway, there's not really a reason for me showing you this. Now, okay, the last part of the talk here is about words. So for me, the word word means a word where the letters are numbers. Okay, the word word means a word where the letters are numbers. In other words, a word is like a permutation, but you can have repeats. You can have numbers repeating in the permutation, so they can repeat themselves. And I should mention that this last part of the talk is joint work with Noah Kravitz, who's an undergraduate at Yale University. And he was a student in the Duluth Research Experience for Undergraduates program this past summer, and I was an advisor at that program, and that's where I got this wonderful pink shirt. So he and I decided to try extending stack sorting to the context of words. And you can do this in sort of the obvious way. You put your word up on this stack and you send it through according to the same rules, saying a number cannot sit on top of something smaller than it. But the question is, can a number sit on top of a copy of itself? Right? If we have a 2 sitting in the stack and another 2 comes along, is this 2 allowed to sit on top of this 2, or does this 2 have to leave before this 2 can go in? And the way we get around this point of ambiguity is we just consider both cases. So first we define an operator fast that sends words to words, and this operates by just sending your word through the stack, but with the convention that a number is allowed to sit on top of a copy of itself. And so in this case, if there's a 2 sitting in the stack and another 2 comes along, then the 2 can sit on top of the other 2. And then we define slow in sort of the same way. We say this time you send your word through the stack, but this time with the convention that a number is not allowed to sit on top of a copy of itself. So this time if you have a 2 sitting in the stack and another 2 comes along, this 2 has to leave before this 2 can go in. And the reason we call them fast and slow is because heuristically you should think fast should be a sort of faster sorting algorithm, in the sense that if you take a word, you can iteratively apply fast to this word until eventually you get to a non-decreasing word. And you can say the number of iterations needed to get to the non-decreasing word, we could call the iteration length of fast on that word. And similarly, you could define the iteration length of slow on a word to be the number of iterations of slow needed to take it to a non-decreasing word. And heuristically, you should think that the iteration length of fast should be less than or equal to the iteration length of slow. And one way you can see this is we can do an example. So we can look at trying to sort 221 with fast. and also with slow. And what's going to happen here, if I do this, is with fast, 2 will go into the stack. And now this 2 can sit on top of the other 2. And now this 1 can sit on top. And now the 1 comes out, and now the 2 comes out, and now the 2 comes out, and we get 1, 2, 2, and that's non-decreasing, and so we're done. It only took 1 iteration to get to the non-decreasing word. But now with slow, what's going to happen is this 2 goes in, and now this 2 forces this 2 to leave prematurely, so this 2 has to come out. Now this 2 can go in, and then the 1 can come in, and then the 1 can come out, and then the 2 comes out, and we get 2, 1, 2, and we're not done. This is not non-decreasing, so we'd have to apply slow again to get to a non-decreasing word. And so this is sort of telling you that what slow does sometimes is it forces this number to leave the stack prematurely. And this premature leaving is in some sense inefficient, and this should lead to slow being a slower sorting algorithm. So Noah and I tried actually proving this, that the iteration length of fast is always less than or equal to the iteration length of slow. And we got really close several times. We tried inducting on like the length of the word and like 3 other things, and we had this huge complicated argument, and we got really close, but we never quite got there, and that's because it's not actually true. So it turns out, first of all, we're not even calling them fast and slow anymore. We're now calling them tortoise and hare. So fast is now hare, and slow is now tortoise, and the reason is we find the fable had it right. Slow and steady wins the race. So there are some examples of words that require more iterations to be sorted with hare than with tortoise. Okay, and so here's an example of a word that requires 4 iterations to be sorted with hare and 3 iterations to be sorted with tortoise.
But before you work so hard, did you test it on many examples?
No. That would have been the first thing.
You could have found out before.
Yeah, we should have done the experimenting first.
Oh.
That's the moral of the story. Yeah. So again, the tortoise and the hare has a good moral here, but not the same as in the original fable. But anyway, yeah, so what really happens here is hare gets off to a really fast start, but then it slows down. And tortoise is getting off to a slow start, but then it steadily creeps up and ends up winning the race. So it's just like the tortoise and the hare. So that's why we call them tortoise and hare. And, okay, the last thing I want to say here is that for every integer in at least 3, we've constructed a word of length 2n plus 1 that requires 2n minus 2 iterations to be sorted with hare, but only n iterations to be sorted with tortoise. And so this is saying the gap between the iteration lengths of hare and tortoise can actually be arbitrarily large, so tortoise can be arbitrarily faster than hare. And we also have a conjecture, and basically what this conjecture is saying is that this construction that we've given is optimal in the sense that you can't find a shorter word that gives you the same gap between the iteration lengths of hare and tortoise. That's basically what this is saying. It's saying the construction is optimal in the sense that you can't find a shorter word that gives you the same gap between the iteration lengths of hare and tortoise. Okay. So, all right, that's everything that I wanted to say. So, yeah, thank you very much. And right, so I have this thing. You can order the letters in thanks alphabetically with the convention that exclamation point is the largest, and you can send it through the stack. And the interesting thing here is that if you do this, if you make this convention on the ordering, then thanks exclamation point is actually a uniquely sorted permutation. So there's only one thing I could have put here at the beginning in order to get thanks exclamation point at the end, and that one thing is key exclamation point H naps. So anyway, that's all. Thank you very much.
Beautiful talk. Colin will be there to answer questions in private, and everybody.